So I want to start with the difference between a Taylor series and a Taylor polynomial. We spent a lot of time talking about Taylor polynomials, and when we talk about a Taylor polynomial, that is a finite number of terms. When we use the word Taylor series, that is an infinite amount of terms. Okay, so a few days ago, we learned how to find a Taylor polynomial, and we're going to take that same exact formula to now talk about Taylor series. Guys, the formula isn't any different. So we're still going to go f of c, where c is our center, f prime of c, x minus c to the first power, f double prime of c over 2 factorial times x minus c squared. And instead of being a finite number of terms, this is actually going to continue forever and ever. Now, the general format is going to be the series starting at the 0th term to the infinity power, or excuse me, stopping at infinity, the nth derivative centered at c, x minus c to the nth power over n factorial. And this is our general term formula. Okay. Now, should that be centered at 0, we call it a Maclaurin series. And we've already kind of talked about the difference between Taylor series and Taylor polynomials and Maclaurin polynomials. Really, the AP exam doesn't make a whole ton of difference. They're going to call a Taylor centered at 0 a Taylor centered at 0, but just to give Mclaren due credit, if it's centered at 0, it's a Maclaurin series. Honestly, I don't make a difference between the two formulas. I remember the Taylor series formula, and I don't make a distinguished difference if it's centered at 0. So let's do a couple of examples. Find a Taylor series for the function f of x e to the 5x centered at c equals 2. Give the first 4 non-zero terms and the general term. Important, they're going to ask you for that general term. So let's think about what we need to build this Taylor series. We're going to need all of the derivatives. So let's start. We have f of x is e to the 5x, which means the first derivative is going to be 5e to the 5x because of power rule. The second derivative is going to be 25e to the 5x because we're multiplying by another multiple of 5. The third derivative, if I multiply by another 5, is going to be 125e to the 5x. I'm going to stop there because it says the first 4 non-zero terms, and this is going to give me 4 zero terms, but I need a formula for the derivative in general. Notice that it's always going to be a power of n and e to the 5x, okay? Now, these have to be evaluated at the center because each one of these in the formula is evaluated at whatever value of c. So let's evaluate them. If I evaluate f of 2, I'm going to get e to the 10th power. F prime of 2 is going to be 5e to the 10th power. F double prime of 2 is going to be 25e to the 10th power. F triple prime of 2 is going to give me 125e to the 10th power. And therefore, my general term evaluated at 2 will be 5 to some power e to the 10th power. So now we're ready to write our Taylor series, okay? And keep in mind, it asks for the Taylor series, first 4 non-zero terms, and the general term. So using the formula up above, remember it's f of c, f prime of c times x minus c, f double prime of c over 2 factorial, x minus c squared, plus dot, 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 all the way forever and forever into your general term. So let's do that. Our first term is going to be e to the 10th power. Our second term is going to give us 5e to the 10th power, but don't forget there's also an x minus 2 to the first power. our next term is going to give us 25e to the 10th power divided by 2 factorial. Don't miss that 2 factorial. X minus 2 to the 2nd power. So we now have 1, 2, 3 terms. I need the first 4 non-zero terms, so we need another one. 125e to the 10th power. Now we're dividing by 3 factorial. X minus 2 to the 3rd power. And this continues on forever. And now it asks us for the general term. So here is our general term. We're going to have that 5 to the nth power, e to the 10th power, and that's going to take care of our derivative, divided by n factorial times x minus 2 to the nth power. And you need to tack on a plus dot, 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 because this is a series. It's going to go on forever and forever, okay? I could also write this in its condensed form. It didn't ask me to do that, but I can write this in its condensed form. I'm just going to draw an arrow over here and say that this is equal to the sum from n equals 0 to infinity of 5 to the n, e to the 10th power, x minus 2 to the nth power over n factorial. Where did I get that from? Hello, that's just your general term. The general term is the formula for the series. Okay, so in fact, there are actually 3 special series that you must know. You're going to have these memorized for the AP exam. So let's talk about these 3 special series, and we're going to derive them. So I want to start with the series for e to the x. So using the pattern that we just did, let's actually derive the series for e to the x. So remember, we need f of x. We're going to need the first derivative, the second derivative, and because I realize this is always going to be derivatives of e to the x, its derivative will always be e to the x. Now we're evaluating this as a MacLaurin series, so that means that the center C is going to be 0, so we need to also evaluate these at 0. F of 0 is going to be 1, f prime of 0 is going to be 1, f double prime of 0 is going to be 1. Hot dog, all the nth derivatives evaluated at 0 are always going to be 1. So now, using our formula, let's actually build this series. Remember that our formula says it has to be f of c, f prime of c times x minus c to the first power, f double prime of c over 2 factorial times x minus c to the second power plus dot, dot, dot. And then that general term is the nth derivative of c over n factorial, x minus c to the nth power, on forever and forever. So, filling this out, going term by term. F of c is 1. F prime of c is also 1. X minus 0. The next derivative is going to give me 1 over 2 factorial x minus 0 squared. And this pattern is going to continue to basically I have my nth term is going to be 1 over n factorial x minus 0 to the nth power forever and forever. What this tells me is that this series is going to be 1 plus x squared over 2 factorial plus x to the third over 3 factorial. And this pattern is going to continue forever and forever and be x to the n over n factorial plus dot, dot, dot. Now, where will this be valid? So, okay, let's ratio test this to find the interval of convergence. Remember that for the ratio test, we're going to take the limit as n approaches infinity. We're going to say, take this term right here, and we're going to go x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. Doing a little bit of manipulation, let's go ahead and multiply by the reciprocal. So we have x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. If we reduce those factorials right here, what that's going to leave me with is I'm going to have an n plus 1 on the bottom. And if I also reduce my x to the n plus 1 and my x to the n, remember that n plus 1 minus n is just going to be 1. So that will result in an x right there. Okay. So now, to remember to find this interval of convergence, we want to take this x right here and we want to move it to the outside because the limit only depends on n. If I take this limit, that limit right there is going to give me 0. And anything times 0 is always going to be 0, and 0 is less than 1. So what does this mean? It means that the interval of convergence is from negative infinity to infinity. The radius of convergence is infinity, and so this thing is valid for all real numbers. So this is an approximation for the function e to the x. Okay. I want you to actually build the series for sine using the exact same pattern. So I'm going to actually ask you to press pause and go through the process of building the series. Okay, so we're back. Let's do it. Remember, if f of x is sine, then my derivative will be cosine. My next derivative is going to be negative sine. My next derivative is going to be negative cosine. Let's go ahead and do the fourth derivative, which will be sine. And this thing obviously is going to continue. Let's evaluate these at the center of 0, since it's a Mclaurin. So f of 0, sine of 0 is 1. F prime of 0, cosine of 0 is 1. To me, f of 0 is 0. F double prime of 0 is going to be 0. F triple prime of 0 is going to be negative 1. And then the fourth derivative at 0 is going to be 0. So what do we notice is that the even powers go away, because we're going to be multiplying by 0. So let's build it using our formula. Remember that our Maclaurin formula says that we're going to take f of 0 plus f prime of 0 times x minus 0, since the center is 0. F double prime of 0 divided by 2 factorial times x minus 0 squared, so on and so forth. So let's do it. F of 0 is 0. F prime of 0 is 1 times x. We're going to get f double prime of 0, which is going to be 0 times x squared over 2 factorial. If I continue in this pattern, the next one's going to be negative 1 times x cubed over 3 factorial plus dot, dot, dot. So all of my odd powers, even powers are going away, and the odd powers are the ones that remain. So let's look at the pattern. We're going to get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And we're going to keep alternating positive, negative, positive, negative. It's going to be odd powers. Now, how do we write our general term? Let me show you. Since it's alternating, we're going to say negative 1 to the nth power. Since it is odd powers, we're going to say x to the 2n plus 1 to yield the odd powers. And since the denominators are always odd powers, we're going to say 2n plus 1 factorial. Make sure you include your plus dot, dot, dot. Again, I want to show you how you can find this interval of convergence for this. So let's do that. We're going to use our ratio test, and we're going to ratio test this formula right here. So we're going to go limit as n approaches infinity of -1 to the n plus 1, x to the 2 n plus 1 plus 1. Be careful there, I kind of squished it in. Over 2 n plus 1 plus 1 factorial. And then remember, we're going to divide by our original formula, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. I apologize if you can hear my screaming baby in the background. Let's simplify this gross, nasty thing. Okay? I have -1 to the n's, and to be honest with you, those -1 to the n's, by the time that we take the absolute value of them, they're not going to matter. So go ahead and get rid of them. We don't need those. Let's simplify this thing right here. That's going to be 2n plus 1 plus 1, so that's 2n plus 2 plus 1, so 2n plus 3. Okay? And then this thing right here is going to become 2n plus 3 factorial. We're going to have our multiply by the reciprocal, so we'll get a 2n plus 1 factorial in the numerator, and an x to the 2n plus 1 in the denominator. If I simplify my factorials, I can't show that here, but remember we've done a little bit of simplification of factorials before. So what that's going to leave me with is I'm going to have just a 2n plus 3 and a 2n plus 2 in the denominator. If I take my 2n plus 3 and my 2n plus 1 and I subtract those, 2n plus 3 minus 2n plus 1, that's 2n plus 3 minus 2n minus 1, which is going to be x squared. Okay? Remember, we're going to take the x squared to the outside because the limit only depends on the n's, so 2n plus 3, 2n plus 2. As this gets really big, that's going to go to 0, and then 0 times anything is 0, and that is always less than 1. Therefore, this thing works for all real numbers. Gross. Now, I'm not going to go through the process of deriving cosine because I think you get the idea here. If you'd like to press pause and go ahead and go through that process, which I'd encourage you to do it. What you're basically going to find is similar to the previous one. Now, the odd powers are going to be missing. And so that's going to result in the following approximation. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... And because this is also alternating, the nth term formula we're going to write as -1 to the n. Since these are even powers, we're going to say x to the 2n over parentheses 2n factorial plus ... And this is valid for -infinity to infinity. Now, you're going to want to know the general terms for all of these. So not only are you going to have to memorize these 3 approximations, 1, 2, and 3, you need to know their formulas for their general terms. Okay. Now, there are other expansions that you might discover if you go and take a College Cal 2 course. We don't talk about them in this class as much for memorization purposes, but there are formulas for 1 over x, for 1 over 1 plus x, 1 over 1 minus x for the natural log. All of these are valid approximations that you could see in a College Calculus 2 class. There are a couple of techniques, though, that we're going to be doing and the AP exam expects you to know how to do. For instance, they might ask you to substitute into a series. They might ask you to multiply or divide the series by a constant or a variable. They could ask you on the AP exam to add or subtract 2 series, or they could ask you to differentiate and integrate a series. So let's do an example of a couple of different terms. So if I wanted a series for sine of x squared, you want to start with sine, okay? So if the series for sine can be approximated by, remember odd powers, first power, x to the third over 3 factorial, x to the fifth over 5 factorial, plus, it's a minus, minus x to the 7th over 7 factorial plus ... Go ahead and write out the general term. It's going to help you because we're going to sub into the general term as well. X to the 2n plus 1 over 2n plus 1 factorial. Don't forget your plus ... since this goes on forever. Now, if the only difference is the fact that this is x squared, what I want to do is I want to sub x squared everywhere that I have an x. So basically, instead of sine x, we're going to have sine of x squared, and we're going to go term by term. So I'm going to have x squared minus, and instead of x cubed, we're going to say x squared cubed. Notice I'm filling in the exterior first. Minus let's fill in that x squared right there. And again, use a general formula. -1 to the n, something to the 2n plus 1 over 2n plus 1 factorial. And instead of x, we're going to write an x squared. Now, I do want to simplify this because I think it's going to make our life a little bit easier. So let's simplify this before we answer the next question. That means that the sine of x squared is going to become x squared minus x to the 6 over 3 factorial. Remember, we multiply those exponents. And what I love about this is that you can actually go ahead and manipulate the general term and go, hey, that's going to give me x to the 4n plus 2 over 2n plus 1 factorial, and this goes on forever and forever. Now, a question they could ask you after doing this is they could say, hey, you know what? We want you to now find a MacLaurin series for the derivative. Now, what is the derivative of sine of x squared? Well, the derivative of sine of x squared is cosine of x squared times 2x. And now we're going to take the derivative of each of our terms. So the derivative of x squared is 2x. Keep your coefficients. That's my caution here. So keep this 1 over 3 factorial. Take your derivative, 6x to the 5th power. Keep your coefficient, 1 over 5 factorial. Take your derivative, 10x to the 9th power. Keep your coefficient, 1 over 7 factorial.